Okay, let us start. So, in the last class we extended the functional calculus to L infinity functions, that means bounded functions. We proved that f going to t sub f, where f was a bounded function, t sub f gave us a bounded operator on the Hilbert space, and this correspondence was an algebra homomorphism which respected the star operation. So, we have a star algebra homomorphism from bounded functions on sigma to bounded operators on the Hilbert space H, right. And there were two more assertions in the theorem. One was that if you have a bounded operator S that commutes with all operators T sub f, where f comes from the smaller algebra, that is continuous functions, then it actually commutes with T sub f for f coming from the bigger algebra, which is the bounded functions, right. So, we have to prove that, and there was also something about the convergence, right. If f n converges to f pointwise and boundedly, then T sub f n converges to T sub f in the weak operator topology. As I said, we will see that it is actually converges in the strong operator topology, but that is something which will come later. Okay. So, right now we will do with this. Okay. So, let us prove those assertions. Suppose S commutes with T sub f. Okay. So, T sub f now for every f in C sigma, right. I want to say that it is it will commute with everything from bounded functions, right. So, it commutes. So, these things are in the algebra A, right. So, this is sitting inside the algebra A. Okay. So, we get, well, what do we get? We get, so look at integral over f d mu, okay. So, maybe let me write this again, u comma s star v. Okay. So, this is S, remember, is a bounded operator, right. So, S star v. So, this is T sub f acting on u inner product with S star v, right. So, this is equal to S star, you can take it to the other side, you will get S T sub f u inner product with v, right, which is equal to S commutes with T sub f. So, I am taking f from C sigma. So, S commutes with T sub f. So, this becomes T sub f S u v, right. So, which I can write in terms of the integral. So, integral over sigma. So, there was always a sigma here as well, this is f, and we have these vectors S u and v, right. So, that is d mu S u comma v, right. So, for all continuous functions f, we have these two measures to be the same, right. So, we get, because S commutes, the bounded operator S commutes with all T sub f's, we get this. So, d mu u S star v is equal to d mu S u v, right. All right. So, we get this. Now, we can go to all. So, so this is an argument which you saw just now. You prove that two measures are equal, and then you can integrate against any bounded function, right. So, starting from continuous functions, you prove two measures are equal, then you can integrate against any bounded function and deduce what you want. Okay. So, hence for any f in B sigma. Okay. So, now I am taking a bounded function, not a continuous function anymore, bounded function, we get using this, right. We get integral over sigma f d mu u S star v, right. So, that will have to be equal to integral over sigma f d mu, other side is S u comma v, right. Okay. So, let us look at this equality again. So, on the left hand side I have T sub f, okay, acting on u comma inner product with S star V, right. That is the, so this is the first vector, this is S star V is the second vector, and so I have T sub f acting on the first vector, inner product with the second vector is equal to T sub f acting on the first vector which is S u, inner product with the second vector, right. So, now this S star I can take it to the other side, right. So, this is equal to, so let me write it here, S T sub f u v, right. So, it is u and v here, similarly u and v here. So, this implies S T sub f equal to T sub f S, but for which f? For every f bounded, right, because we started from there. So, S commutes with everything in every T sub f where f runs over bounded functions, right. Starting from continuous functions, we were able to push it to bounded functions. Okay. So, that is one assertion. The other assertion is about the pointwise and boundedly convergent, right. Now, suppose, so finally let f n converge to f pointwise boundedly, right. So, that means f n x converges to f of x for every x. So, f n x converges to f of x for every x in sigma, and all of them are bounded, right. So, mod f n is less than, so supremum over n and supremum over x, right. So, this is bounded by some fixed constant k independent of n. Okay. That is what you mean by pointwise and boundedly converging. Then, well, we just want to show that T sub f n converges to, so let me write down that, to show that T sub f n converges to T sub f in the weak operator topology, right, in the weak operator topology. Okay. What does that mean? Well, that is a trivial statement now, because of whatever we have done already. I look at T sub f n inner product acting on u, inner product with v, right, and I want to say that this converges to T sub f acting on u, inner product with v, right, but that is trivial now, because this is simply by definition integral over sigma f n d mu u v, right. So, d mu u v is a complex measure, complex finite measure. So, its norm is less than to norm u times norm v, and f n converges to f pointwise, and all the mod f n's are bounded by some constant, and these are, this is a finite measure. So, that constant is actually in L 1, and so dZt will apply, right. So, you apply dZt, remember these are complex measures. So, you have to write it as a use the polar form, right. So, you write it as something times a positive measure and then apply dCt, right. So, integral over sigma f d mu u v, which is equal to T sub f acting on u, inner product with v, right. So, that is that is easy. So, convergence in the weak operator topology follows immediately, but we will see that it actually converges in a much stronger form in the strong operator topology. Okay. So, let us continue. So, just to recap, starting from a commutative C star subalgebra with identity of B of h, which got identified with continuous functions on the spectrum, that is phi sigma via the Gelfand transform, we managed to look at a slightly bigger algebra, that means looking at all bounded functions on sigma, we got these operators T sub f using these measures, right. Now, we look at some special bounded functions which are indicator functions or characteristic functions of subsets of sigma, okay, and see some properties there. Okay. So, if E is contained in sigma is a Borel set, let chi E, so chi E is the characteristic function, okay. So, be the characteristic function of E, that means it is 1. So, that is chi E at x is equal to 1 if x is in E, 0 otherwise, right. that is what you mean by a characteristic function or an integrated function. Okay. Define. So, if I take any bounded function, I have an operator, right. For f I denoted it by t sub f. So, for chi e I have t sub chi e, right. So, that I define p of e to be equal to t chi e. Okay. So, this is a bounded operator. So, let us look at the properties of this. Okay. So, theorem E going to P of E. So, where is this? This is a map from the Borel sigma algebra of the spectrum sigma to bounded operators on H, right. So, the script B on the left hand side is the Borel sigma algebra. When we say bounded, we do not use the script B, just normal B. Okay. So, E going to P. So, what sort of a map is that? Any set gives me an operator. Okay. So, any function gave me an operator, that was what we did. Now, we are looking at a set giving an operator via taking the indicator function of that set, right. So, E going to P of E has the following properties, has the following properties. Okay. Each P of E is an orthogonal projection, is an orthogonal projection. Well, what does that mean? So, it is orthogonal meaning projection meaning it is P E equal to P E square, right. So, that means it is a projection. Orthogonal projection meaning kernel and range are orthogonal to each other, which is same as saying it is self adjoint. So, it is a self adjoint projection. Okay. Okay. So, B P of phi equal to 0, P of the whole space equal to the identity operator. Okay. So, P of empty set is 0, which is trivial. P of the whole space is identity. C P of E intersection F equal to P E intersection P F, where E and F are Borel subsets of the spectrum sigma. Okay. So, whenever you write P of E, E is assumed to be a Borel subset. I may not keep saying that. D, if E j, j equal to 1, 2, 3 etc. are disjoint Borel subsets, or disjoint Borel subsets of sigma, then we have a certain summability property, that is P of union E j. So, I am taking the disjoint Borel subsets E j and taking the union, right. So, this is sum of P E j, j equal to 1 to infinity. So, on the left hand side is a projection, right, P of some set, that is a projection. On the right hand side I am adding projections, right, it is an infinite sum. So, I should tell you what is the convergence in the strong operator topology, in the strong operator topology. Okay, that means I take, so on the right hand side I take the partial sums up to let us say k, j equal to 1 to k p e j, act it on a vector x or v, that will converge to this sum which is p of union e j. Okay. So, that is the assertion, right. So, convergence is in the strong operator topology. So, if you look at it carefully, you see that it has properties of measure, right. The first one is of course projection thing. Second one says it is like a probability measure, right. The empty set of course has measure 0, the whole set, whole space has measure 1, but here 1 means it is the identity operator, right. So, it is not a measure in the usual sense, it is a projection valued measure, right. So, the measure is sort of taking values in the projection space of projections, right. Projections are operators and we are looking at projection valued measure in some sense. C says P of A intersection F equal to P E intersection P F. So, that is sort of saying if you take disjoint sets E and F, to be disjoint, then the product is 0, which means the range are orthogonal to each other, right. So, disjoint sets will go to projections whose ranges are orthogonal to each other, and D is the countable additivity, right. If Ej are disjoint, so they are disjoint, remember that, then the measure of the union is the sum of the measure of individual sets, right. But the sum, now that we are in the space of operators and so on, the sum has to be interpreted appropriately, and that is in the strong operator topology, right. So, you act it on any vector, you will have the convergence property. Okay. So, let us prove this. So, such a thing, we will define this such a thing to be a projection valued measure. I will write down the formal definition. So, okay. So, proof. So, most of this is sort of straightforward from whatever we have already done. So, how do you show that P of E is a orthogonal projection? Well, what is P of E? So, let us recall its definition. P of E is nothing but T of chi E, right. For each bounded function, I have this operator, and that map f going to T sub f was a star algebra homomorphism, right. So, if I look at chi e, I know that chi e is equal to chi e bar, right, because it is 1 and 0, is also equal to chi e square, right. So, from the algebra homomorphism property, this implies that P of E, so that is the left hand side, right, chi e bar should go to the adjoint of the operator, right. So, that is P e star, right, and chi e square should go to P e into P e, right, because of the algebra homomorphism property. So, that is P e square, right. So, P e is an orthogonal projection. So, that follows immediately. So, that was A. B, P of empty set is 0, well, because the chi empty set is the 0 function. So, 0 goes to 0, and P of sigma, well, what is this? This is T of chi sigma equal to the identity operator, because chi sigma is the identity function, is the constant function one, right, is the constant function 1, right, and 1 has to go to 1, right. So, let us write this clearly. So, this is chi sigma, right, because it is an algebra homomorphism and so on, 1 has to go to the identity operator. So, that was obvious. C is also obvious. We want to prove that P of E intersection f is P E times P f, but that is trivial, because chi of E intersection f is equal to chi E times chi f, right. That is one advantage about indicator functions. This becomes the product, and so the map E going to P E is an algebra, I mean T f going to T sub f is an algebra homomorphism, tells me that P of E intersection f equal to T of chi E into chi f, right, equal to P E P f, right, because it becomes the product of T chi E and T chi f, and that is P E P f. So, the only thing to prove is the final one, which is the countable additivity. Okay. So, that requires some work. For any n, let us define f of n to be union E j, j equal to 1 to n. So, I am cutting it at the nth place, right. Then if I look at chi of f n, what is chi of f n? So, that is the indicator function of f n. Remember, E j's are disjoint, right. So, this is simply the sum of j equal to 1 to n chi E j, right, because E j's are disjoint, E j are disjoint. And what happens to chi f n? Okay. So, chi f n, so as n increases, f n increases to the union, right. So, chi f n converges to chi f pointwise surely, because if I take an x, well, what is f? F is equal to union E j, j equal to 1 to infinity, right, that is a full union. So, chi f n will converge to chi f pointwise, and all the chi fn's are bounded by 1, right. So, this convergence is P dot B, right, that is pointwise and boundedly. And so, if chi fn converges to chi f pointwise boundedly, we know that T of chi fn will converge to T chi f in the weak operator topology. We proved that, right. If fn converges to f P b, then we have T fn converging to T f in the weak operator topology. Okay. So, let us write down that. So, T chi fn converges to T chi f in the weak operator topology. The weak operator topology, which is same as this is what is T chi fn, that is P of fn, right, that is P fn. Well, what is P fn? Okay. So, I should write this a bit more clearly, use this and use the fact that T T respects linearity. So, T chi fn is equal to summation j equal to 1 to n T chi e j, right. So, P fn is going to be summation j equal to 1 to n P e j, right, because of this, right, that is the definition of P, right. So, P is linear when you have disjoint sets, right, that is essentially the finite additivity of the measure, right. So, that is what we have trivially we want to show that countable additivity holds with in the strong operator topology, okay. And P fn converges to P f in the weak operator topology. Okay. So, also, so let us write down this f equal to fn union f minus fn, and this is a disjoint union, right. So, fn is only up to n and f is the whole union. I throw out fn and then write it as fn union f minus fn. So, that is a disjoint union. Okay. So, again because of additivity chi f will be chi fn plus chi f minus fn, and I take apply use whatever we have earlier. So, P of f would be equal to P fn plus P of f minus fn. Okay. We will use this. Okay. So, now what do I want to show? I want to show the convergence in the strong operator topology, right. So, I look at P f minus P fn acting on u and I take the norm square, right. P fn is the sum, right, summation j equal to 1 to n P e j acting on u. I want to say that it converges to P f, f is the whole union, right, j equal to 1 to infinity in the strong operator topology. So, I want to show that this expression which I have written goes to 0. Okay. So, let us see, this is nothing but use this P f minus P fn is nothing but P of f minus fn, right, whatever is remaining in fact acting on u square. Okay. But this is a projection, right. So, projection so if P is a projection, P u norm of P u square is P u inner product with u, right. So, this is P of f minus fn u inner product with u, right, because P of f minus fn is a projection. Strictly speaking, I should have P f minus fn u inner product with the same thing. So, on the right hand side I have P, I can bring it to the left hand side, that is P star, but P star is P. So, and P square is P, right. So, I will get this equal to, now I can use whatever we have here again, P f minus fn is P f minus P n P fn u inner product with u, right. So, let me write one more step, P f u u minus P f n u u, and that goes to 0, right, because now it is the weak operator topology, right. I know that P f n converges to P f in the weak operator topology, that means P f n u inner product with v will converge to P f u inner product with v, right. Here v and u are same, that is all. So, this goes to 0, and so this is what is going to 0, right. Hence, Pfn, which is equal to summation j equal to 1 to n P of Ej converges to P union Ej, right, j equal to 1 to infinity in the strong operator topology, right, in the strong operator topology. Okay, so that proves all that was asserted in the theorem. Now let us write down an easy corollary which should remind you of certain things from finite dimensional spectral theorem. So if, which I had mentioned actually, E intersection F is empty, then Pe times Pf equal to 0. That is trivial because if E intersection F is empty, P of E intersection F is 0, right. So, P of E intersection F is equal to Pe times Pf, right. And E intersection F is empty. So, P of empty set is 0, and so this we have. So, this you should compare with what you have seen in the case of finite dimensional spectral theorem. E and F are coming from are Borel subsets of sigma, right. Sigma is the spectrum. So, in the finite dimensional case, the spectrum is the set of eigenvalues, and if they are disjoint, that means you are looking at distinct eigenvalues, and you are looking at projections to those eigenspaces, right. The Pe and Pf are going to be those projections to those eigenspaces, and they are orthogonal. That is same as saying, if for a normal operator, if I take two distinct eigenvalues, the eigenvectors corresponding to them are orthogonal to each other. Okay. So, that statement is what is being reflected here. Okay. So, what we do now is to formulate the properties of P we have just seen, which is the projection, in an abstract setting. Okay. So, we formulate the properties of P in an abstract setting, Okay. So, there may be a slight difference in the notation when I write everything in the abstract setting. Let omega be a set and script f be a sigma algebra. Okay. So, what you should keep in mind is your omega is going to be the spectrum, right, that is sigma. F is, let us say, Borel sigma algebra of the spectrum sigma. Okay. A sigma algebra of subsets of omega. H is a Hilbert space. H is a Hilbert space, and we define a projection valued measure. So, if you look at what we have proved and remember where it came from, we started with a C-star subalgebra, commutative C-star subalgebra of B of H with identity, used Gelfand transform, extended it to bounded functions. Among bounded function, we chose those indicator or characteristic functions of subsets that gave us a map from subsets, Borel subsets of the spectrum to projections. Now, we proved some properties of those projections, and now we are going to put that as a definition. Okay. So, that is how we extractify these properties. So, a projection valued measure, So, the projections are going to be on H, right, the Hilbert space is H. So, one should say H projection valued measure, I will skip that. So, the Hilbert space, underlying Hilbert space will be always clear. So, a projection valued measure on omega f, right. So, omega is my set, f is the sigma algebra of subsets of omega, is a map, it is a map P from script f to bounded operators on H, such that it has all the properties we have just seen, right. So, A, if E is in script f, then P E equal to P E star equal to P square, right. That means it is a orthogonal projection, right. We want that property to be true, right. So, we saw this property when we defined something earlier, making that into a definition. B P phi equal to 0, empty set goes to 0, the whole space goes to identity, C intersection. So, this is some sort of independence, but it is clear what is happening. As I explained earlier, this simply says that eigen spaces corresponding to distinct eigenvalues are orthogonal to each other, that is that property C. Union E j, j equal to 1 to infinity equal to E, disjoint union, then P of E equal to summation P E j, j equal to 1 to infinity in the strong operator topology, right, in the strong operator topology. Okay. Okay. So, we will stop here. We have defined this object called projection valued measure. So, let me quickly recap, starting from a commutative C star subalgebra with identity of B of h. We managed to extend the Gelfand the properties of the Gelfand transform, right. From using the Gelfand transform, we extended the functional calculus to bounded functions that gave us these projections. Now, we are going to study them as separate objects. So, look at a projection valued measure which has all these properties, that means you have this convergence in the strong operator topology, which is like the countable additivity of a measure, that is why it is called a projection valued measure, right. And question is, can you define operators, right. So, we will sort of reverse the procedure which we did so far, starting from the C star algebra and so on. We went into projections. Now, we are going to start from the projection valued measure, we will define. So, it is like in it is like developing the integration, right. So, P of E is like the integral of chi E, right, but we are getting projections, not numbers. But once you have it for chi E, you can define it for simple functions and extend it to all measurable bounded measurable functions, right. So, that way we will reverse this procedure, that is what we will do next. Okay. So, let us stop here.